So, you know how complicated chemical reactions can seem? Well, today we're going to decode them because it turns out there's this kind of secret map that makes it all click. Seriously, just forget about memorizing all those endless rules and reagents and outcomes. What if, and just hear me out, what if every single reaction followed the same simple story? A framework that could explain why something happens and how fast it happens. Well, there is. And it's not a set of rules you have to memorize. It's a story. It's a journey. Yeah, think of it like a simple hike from one valley, over a mountain, and into the next. And this simple analogy is everything. It's the key. If you think of a reaction as just a little mountain trail, suddenly you can unlock the whole puzzle. You can understand why reactions happen in the first place, how fast they go, and even how we can control what happens. Okay, so first things first. Before we can start this hike, we've got to learn how to read the map, right? This first part is all about thermodynamics, and that answers the most basic question of all. Why does this journey even happen? You can think of this slide as our Rosetta Stone. It's literally translating all that abstract chemistry jargon into the physical journey we're talking about. So, stable molecules, those are just the valleys, safe, no-energy spots. And a reaction mechanism, that's not some complicated list of steps anymore. No, it's just the path you have to walk to get from one valley to the next. Now, the single most important thing on our entire map is the overall slope. In chemistry, they call this Gibbs free energy, or just delta G. And all you need to know is that this one value tells you if your hike is basically going to be downhill or uphill. So here's the bottom line. If that delta G is negative, the trail goes downhill. The reaction is what we call spontaneous. It just happens. It'll go all on its own, like a ball rolling down a hill. But if delta G is positive, well, now you're hiking uphill, my friend, and you're going to need to pump some energy into the system to make it happen. Okay, but here's the catch, right? Just because you know the trail goes downhill overall, that doesn't tell you anything about how fast you're going to get to the bottom. For that, we have to look at the actual climb. And this is the world of kinetics. See, even on a journey that's mostly downhill, there's almost always a little hill you've got to climb first to get started. And that hill, that's the activation energy. It's pretty simple. The higher the hill, the more energy it takes to get over it, and the slower the whole thing goes. A little hill, you're looking at a much, much faster reaction. And this is such a great way to understand what a catalyst actually does. It's not magic. A catalyst doesn't change where you start, and it doesn't change where you finish. All it does is find a shortcut. It's like it carves a tunnel right through the mountain. It gives you a brand new path with a way smaller hill to climb, so the whole journey just happens, well, dramatically faster. All right, so we get it. We know why reaction happens. That's thermodynamics. And we know what controls its speed. That's kinetics. But what happens when the map shows like 2 or 3 different trails leading out of your starting valley? Which one do you take? This is where chemistry gets really, really clever. So to get a handle on this, the sources give us this great little story about 2 hikers, chlorine and bromine. Now, they're both trying to react with the exact same molecule, but they go about it in completely different ways. They have totally different hiking styles. Okay, so you've got chlorine. Think of chlorine as the fast and reckless one. Its reaction is super exothermic. It's like a steep downhill sprint. That means it has a tiny little activation hill to get over, so it just goes fast. It takes the first path it sees, no second thoughts. But then you have bromine. Bromine is the slow, careful, selective one. Its journey is actually endothermic. It's an uphill climb. So it's facing this much bigger mountain. It has to be slow. It has to be picky. It only chooses the absolute most stable, lowest energy path it can find. And just look at the result of bromine being so careful. I mean, wow. When it reacts with isobutane, it has 2 possible paths it could take, but it's not even a contest. Look at this. It is so ridiculously selective that it picks one path almost exclusively. We're talking over 94% of the most stable product. It barely even touches the other option. So, okay, why? Why is bromine so picky? Well, the answer is something called the Hammond postulate. And don't let the name scare you. In simple terms, all this principle does is describe the shape of the hill, and more importantly, where the very peak of that hill is located on the trail. Okay, check this out. Because bromine's climb is that tough, uphill endothermic one, the peak of its mountain is late in the trail. It's really, really close to the final valleys where the products live. And from up there, from that high vantage point, it can basically see which of the potential destinations is the most stable one. So of course, it chooses that path. Chlorine, its peak is way early and super low. It has no idea what's ahead. It has no perspective at all. All right, let's get to our final and honestly really fascinating twist on this whole path idea. We've seen what happens when you have to choose between two different paths. But what happens when the path itself leads you to a choice between two destinations that are, well, perfect mirror images of each other? And the best analogy for this is your hands. Just think about it. Your left hand and your right hand are identical, right? Same fingers, same thumb, but they're also mirror images. You can't perfectly stack one on top of the other. Well, tons of molecules are just like that. And in chemistry, we have a word for this handedness: chirality. So, back to our mountain journey. What does this look like? Well, it's like you climb to the top of the peak, and instead of a sharp point, you find a wide, flat plateau. This plateau is a chiral, which is just a fancy way of saying it has no left or right bias. It's symmetrical. And from there, you have a choice. You can go down the front side of the mountain, or you can go down the back side. And because that plateau doesn't have any preference one way or the other, what happens? You get a perfect 50-50 split. Half the molecules go down one side, half go down the other. The reaction creates both the left-handed and the right-handed versions of the product in exactly equal amounts. And this isn't just some neat little chemistry trick. This simple idea is absolutely fundamental. It's a huge piece of the puzzle for understanding how life itself, which is almost entirely one-handed, could have even started. And that brings us to our final takeaway. And this one's a little different. It's a strange kind of cryptic note that was found scribbled in the margins of the source material. A little fragment that tries to link this very chemical idea to the entire cosmos. Now, the note doesn't really explain itself, it just leaves us with this huge question. What if the universe itself has a preferred handedness? Think about it. If the basic rules of chemistry are all built on these kinds of simple, mirror image choices, then maybe the biggest, most mysterious structures in the cosmos are built on them too. What if the asymmetry between matter and dark matter is just the ultimate expression of this chirality? What if the whole universe is just following a path on some final ultimate energy map?